Hi there, welcome to my lesson on current, voltage, and resistance. And we're going to deal with Ohm's law. Let's review current. One thing we should have found out about our lab that we did the other day was that when we look at current along a circuit that has just one path, if we take an ammeter and we hook it up as part of the circuit, let's say this spot. The ammeter said 600 milliamps with a galvanometer or 0.6 amps with an ammeter. And so let's move it somewhere else. Let's put it at a different location. And what did we find out? It's the same. So let's move it over here, and what will happen is it doesn't matter where the ammeter along a circuit that has just one path, the amount of current or how fast the electrons are passing will always be the same in series. Let's look again. We have a 9-volt battery. Now we've added, compared to this picture where there's just 2 bulbs, let's add a 3rd bulb. Now what do you guess would happen if we measured the current? Remember, it could be anywhere along here. What would you guess? Well, if we add another bulb, what does that do to how fast the electrons are flowing? The analogy might be we're driving along a highway, and what if we increase the number of speed bumps along the highway? What would that do? Instead of having 2 speed bumps, we now have 3 speed bumps. What would that do to the speed of the cars, which are the electrons? It would slow them down. That's right. So if we add a 3rd bulb, the electrons, when the switch is on, will all now have to travel a little bit slower, which means the light is going to be dimmer and the current would be less than 0.6. It was 0.6 with 2 bulbs, so it's probably going to be about 0.4. So if we had 1 bulb, it might be 0.8. So if we can change, what if we change the voltage of the battery now? So we have a much stronger battery. What will that do to the current? Well, the battery is the device that kind of pushes the electrons along, and the stronger the push, the faster the electrons go, so it would probably be higher, maybe 0.8 now. Remember, it was 0.6 with a 9-volt. Let's talk about voltage. Again, when you measure voltage, you have to make sure you're kind of hooking it in parallel. So if we measure voltage across the battery, a 9-volt battery, we should have gotten 9 volts for the voltage. Then we take our voltmeter and we go to different spots along the circuit. And what we should have noticed is as we start at the top of the hill from the plus and we go down the hill, voltage decreases. It decreases in the opposite direction of the flow of electrons. So electrons go this way, a drop in voltage goes this way. As we add more and more loads, we cause the voltage to drop. So if we measure at the end or the bottom of the hill, voltage now will be about 0 volts because there's no more push left. Remember, it's the push that the voltage is providing. So let's look at this again. Let's look at how voltage drops in a circuit. Let's take a 6-volt battery, and if we measure between points A and F, the voltage is 6 volts across the battery. How about from point A to B? So what would, if we took a voltmeter and hooked our wires up this way, there would be no change. How about between point B and C? The voltage would drop by however the resistance is of the battery, so it drops down. And then from C to D, nothing. And then from D to E, it drops again because of the load to the point where we get to point F. From E to F, the voltage is 0. So voltage drops along. Next, I want to talk about resistance. And in resistance, basically slows down the flow of electrons. Any device that slows down the flow of electrons. So that can be a load, so it can be a bulb, or we can buy resistors to do that. And resistors look like this. I'll pull up my picture of a resistor from the first slide. And so here's an example of what resistors might look like inside, say, a computer or a radio device. Now, depending on what the device needs us to do, we might have to slow the flow of electrons, and we'd put these things in here. Also, if we go back to our water analogy, here's the dam, and the water behind the dam, the higher it is, the stronger the voltage of the battery. When it comes to resistance, we might look at what size of hole, what size of hole or pipe is allowing the water to flow out. If the pipe is big and it's a big hole like this, we would say that that's very little resistance. However, if we make the pipe thin, like the wire, that means there's more resistance. There's other ways, other things about resistance. If we deal with water and a river, so if we deal with a river, for example, the flowing river, if we have lots of rocks along the flowing river, so the water flow would be the current, but the amount of rocks that would slow the current down, that might be the resistance. More on resistance on another day. Let's go on to my last thing. We can calculate the three principles that occur within a circuit, the voltage or the current or the amount of resistance. A German physicist, Simon Ohm, came up with a law that governs how these work. And there are three variables to worry about. Voltage is always equal to the current times the resistance, or resistance is equal to voltage divided, current is equal to voltage divided by resistance, or resistance equals voltage divided by current. And so let's see if we can apply that to a circuit. Here's a circuit, and here's Ohm's law, or one version of it anyway. I equals current in amps, V is voltage in volts, and resistance is always in the unit ohms. So let's say we have a 4-volt battery, and it's placed in series with a 2-ohm resistor. Ohms has a neat symbol. Here's a symbol for ohms, kind of like that. Okay, what's the total current? So what are we using? We need the formula I equals V over R. What do we know? Well, let's write down what we know. We know V, that's 4 volts. We know R, that's 2 ohms. We just don't know I. So let's solve for I by plugging in our numbers. So let's move over here. 4 volts divided by 2 ohms equals I. 2. 2 what? Well, we need to know this. 2 amps, not milliamps, but capital A for amps. Let's try another one. Here's another circuit. We have a 36-volt battery. We find out that this is I, the current is 4 amps. Remember, in series, it doesn't matter. We could take it here, here, anywhere. The current's always the same in a series circuit like this. But we don't know R. So, well, originally we know I equals V over R, but that won't work. So let's move the formula around. R also equals V over I, and that's the form of the formula we need. What's V? 36 volts, and we divide by I, which is 4 amps, capital A, and that equals 9. 9 what? 9 ohms. And so there's the answer. One more. So current, how much current is flowing through this? So 12-volt battery, 3 ohms for a bulb or a resistor, and we don't know I. So back to our formula, I equals V over R. So that means 12 divided by 3. And so I is 4. For what? We need our units. Don't forget your units. 4 amps. Okay, let's try and find resistance now. So Ohm's law now would be R is V over I. V is 36. I is 6, so 6 ohms. How about V? We haven't tried to solve for V. So V equals I, which is the current, times R. So let's substitute in 6 amps is the I, and the R is 3 ohms. And so 6 times 3, 18 volts. There you go. And so that's my quick lesson on how we use Ohm's law.